Okay, in Chapter 6, we're going to start investigating applications of the derivative. So far, we've learned that the derivative of a function is the slope of the tangent line. And what we're going to do now is look at what are some of the applications of finding the slope of a tangent line. In 6.1, we're going to look at the slope of a tangent line as what's called a rate of change. So what I've done for you here is drawn a picture of a function. So suppose that we have a function y that is a function of x, in other words, f of x. If we were to select some point on the graph of f of x, let's say we called it x1, that point would have a y value, and of course the y value would be the function f at x1. Now as we move along this graph, the function is changing. So let's say we wanted to find out how fast it was changing. So what we could do is pick a second point. So let's say we picked a second point and we called it x2. Now, obviously the y value has changed, and this y value would be f at x2. Now, we know that if we actually calculated the slope joining these 2 points, so if we join those 2 points with a line, we would have what's called a secant line. That secant line would represent the rate of change of the function. In other words, how fast y is changing as we change x. But this would be the average rate of change between 2 points. So we can define the average rate of change. So if we take delta y over delta x, in other words, the change in y over the change in x, that quotient, which we can write as f at x2 minus f at x1, all over x2 minus x1. So this quotient right here would give me the slope of that secant line. That slope is called the average rate of change. Called the average rate of change of y with respect to x over the interval square bracket x1 to x2. So just to summarize, this graph right here, this function f of x, it is constantly changing. If we want to know how fast it was changing, that speed at which it's changing, which we call the rate of change, is nothing more than the slope of a secant line joining any 2 points on the graph. So if we were to select 2 arbitrary points, x1 and x2, then the average rate of change of the function y with respect to x would be the slope of the secant line over that given interval. So I'm going to summarize this by saying that note the average rate of change, is the slope of the secant line joining x1 and x2. We just saw that if you have a function f of x and you want to find the rate of change between 2 points x1 and x2, then what you need to do is find the slope of the secant line joining those 2 points. But in calculus, we're not concerned about average rate of change. What if the question was posed a bit differently? What if we had a point right here called x1, and what if we wanted to know, this time, not the average rate of change between 2 points, but what if we wanted to find the rate of change at exactly x1? Well, you can see that that would just be the slope of the tangent line. If I drew a tangent slope right there, that tangent slope would give me the steepness of the graph at that point, or in other words, we call it the instantaneous rate of change. So to set this up now, we're going to have to, instead of picking x1 and x2, we're going to have to pick a second point on our graph. But just like we did when we developed the derivative, we're going to have to now give the difference between these 2 points a variable. So let's say we called that delta x. So now our second point would be x1 plus delta x. The y value here would be f at x1, and the y value of this point would be the function at x1 plus delta x. Now I can find the secant slope by just calculating the slope between these 2 points. And if I want to find what's called the instantaneous rate of change, all I need to do now is introduce the concept of limits and therefore what's called a derivative. So we have what's called the instantaneous rate of change. The instantaneous rate of change at x1. And the instantaneous rate of change is going to be the derivative. It's going to be f prime of x, our notation for derivative. And what we're going to do is we're going to take the limit as delta x approaches 0 of our secant slope. So our secant slope, of course, would just be f at x1 plus delta x minus the function at x1 all over delta x. Notice that I'm using the same formula I use for average rate of change, except in the case of average rate of change, the x1 and the x2 could not move, and so we were finding a secant slope. But of course, by introducing the limit concept, we can allow the 2 points to come together, and now we have the ability to find not just the average rate of change of a function between 2 points, but we can find the instantaneous rate of change at a given point. And as we know, that's the slope of a tangent line, which we've called a derivative. So just to summarize then, so I'll give you a summary. Number one, the average rate of change of a function f of x between x1 and x2, so the average rate of change is the slope of the secant line, is the slope of the secant line joining x1 and x2. So the average rate of change, we would write that like this. We would say rate of change, I'll put in front here average. The average rate of change is just equal to the function at x2 minus the function at x1 all over x2 minus x1. So that would be the average rate of change. In calculus, however, we're not concerned about the average rate of change. We want to know what the instantaneous rate of change is at a given point. So the second point of our summary here would be that the rate of change, and if you don't see the word average, if you just see the phrase rate of change, we're referring to instantaneous. I'll put in brackets here instantaneous, but usually that word's not written. It'll just say find the rate of change. So the rate of change of the function f of x. Now the difference here is instead of finding the average between 2 points, the instantaneous rate of change of a function is at a point. So the rate of change of f of x at the point x1 is the slope of the tangent line at x1. And of course, the way we would write that is we would say that the rate of change is equal to f prime at x1, which is equal to the limit as delta x approaches 0 of the function at x1 plus delta x minus the function f at x1 all over delta x. So just to summarize, we're now starting to investigate applications of the derivative. And one of the applications is, if you have any function called f of x, if you want to know how fast the function is changing, we call it its rate of change. Before we had the concept of calculus or derivatives, we were limited to finding the average rate of change between 2 points. But using the concept of limits and the derivative, we can change that now to what's called the instantaneous rate of change, which is the slope of the tangent line. So what we'll do next now is we'll look at some examples of what that. All right. right, we're going to look at an example now of a rate of change problem. So I've selected for our first example, one in which an employee is working for a company and their productivity is a function of time. So the question reads, an employee's monthly production in number of units produced M is found to be a function of the number of years of service T. In other words, the longer that the person works for this company, their productivity is changing depending on the year that they've been working. So the function that we're given is M of T equals negative 2T squared plus 100T plus 180. It is not necessary to draw a picture to do these questions, but what I've done over here is drawn a picture for you so you can actually see what the productivity would look like. Our function is a concave down parabola with a m-intercept of 180 if we plugged in 0 for time. So that means that this graph is starting right here at 180. So the employee is producing 180 units initially. As time goes by, their productivity is going to change, as followed by this green graph right here. So the first question says, find the productivity at 10 years. So the first question is not asking a rate of change. It's simply asking how many units was the employee producing at their 10th year. In other words, it's just asking us to find a point on the graph. So I've selected the point T equals 10, plugged it into the function, so M at 10, and it turns out to be 980 units. So on the graph, that would mean that this point 10 corresponds to an M value of 980. So the first question is simply asking for a point on the graph. What's the productivity at 10 years? Now, a question that might be of more interest to an employer is not just what the employee was doing at that particular moment, but was their production increasing or decreasing? So we could find what's called the average rate of change. We could say, find the average rate of change of the productivity between 10 and 20 years. So if I plug in 10 years, the employee was producing 980 units. If I plug in 20 years, it turns out that the employee was producing 1,380 units. That would be M at 20. If I want to find on average what their productivity was doing, it's called the average rate of change, and it's a slope of the secant. This red line right here represents a secant line joining the points 10 and 20. That's going to give me, on average, the rate of growth of the production of this employee. So finding the average rate of change is just a secant slope. It would just be delta M over delta T, which would just be M at 20 take away M at 10 over 20 minus 10, which works out to be 40. But notice the units here. In the first question, the units were just how many objects were being produced. In this case, we called them units. This is a rate of change. This is the number of units per time. So now we're finding that the employee was making 40 units per year more on average between their 10th and 20th year. But it still is only an average. It's not telling us how they were doing on their 10th year or their 11th year or their 12th year. It just tells us that between 10 and 20 years, on average, they were producing 40 units a year more. An employer might want to know precisely what's happening at 10 years. So the last question is, find the rate of change of productivity at 10 years. Now this is a calculus question. This is a slope of a tangent. The slope of the tangent would be this blue line right here, and the slope of that blue line would tell me precisely what that employee was doing as far as their productivity at the 10th year. Well, an instantaneous rate of change is a derivative. So we just take the derivative m prime of our productivity function using the rules we learned earlier, and we get the derivative to be negative 4t plus 10. M prime at 10 years, instantaneous rate of change would just be 60 units per year. So this question takes you through a progression of finding just a point on the graph, finding an average rate of change, and then of course ultimately the purpose of calculus, and that is to find the instantaneous or the tangent slope at that given point using the concept of a derivative. So it turns out that this employee, exactly on their 10th year, was producing 60 units per year more every year. So that now the employer has a very good indication of how that employee was doing at that precise moment. We'll look at one more example of a rate of change problem. This time it's the temperature of a person during an illness. So what we have here is a function that says that the temperature in degrees Fahrenheit of a person during an illness is given by the following function: 4t divided by t squared plus 1 plus 98.6. 98.6 is normal temperature for a person in degrees Fahrenheit. So T is time and the capital T is the temperature. So the first question says, find the temperature at 2 hours. So again, this is not a rate of change question. This is just an algebra question. If we want to know what the person's temperature was after 2 hours, we would just be finding T at 2. So we're not doing a slope here, we're just finding a point. If you plug that 2 into the function, it turns out to be 100.2 degrees Fahrenheit. So the person has a little bit of a fever. But you see, without calculus, we're limited to just finding what the person's temperature is at that moment. What if we were more interested in knowing whether the person's temperature was increasing or decreasing? That's called a rate of change. So the second question says, find the rate of change of the temperature at 2 hours. This would be a question that would be of, I think, a lot more importance than just knowing the temperature. Is the person's temperature still rising? Is it falling? How fast is it rising? This is a rate of change problem. It's the slope of a tangent problem. So what we're going to do here is simply take the derivative. So we're going to take the derivative t prime at t. Now this question is a little more complicated than our previous one. You may recall that we had something called the quotient rule. We have here a function 4t divided by another function t squared plus 1. So we have to apply our quotient rule. Our quotient rule said take the derivative of the numerator, which would just be 4, multiplied by the denominator, t squared plus 1, subtract the derivative of the denominator, which would be 2t, times the numerator, 4t, all divided by the denominator squared. So that would be our unsimplified derivative. Now we're going to have to plug in our value of 2, so we could simplify our derivative. It's good practice for us to do that. So what we could do is distribute through the brackets and get 4t squared plus 4 minus 8t squared all over t squared plus 1 all squared. Collecting our like terms, we would end up with minus 4t squared plus 4 all over t squared plus 1 all squared. So this answer right here, this is our simplified derivative. Pretty powerful thing. This is giving us the rate of change. In other words, how fast the person's temperature is changing at any moment in time during their illness. Now the question wants us to know the rate of change at 2 hours, so we're just going to go t prime at 2. We're going to plug 2 into here, and it ends up being negative 12 over 25. The units will be, we're finding a rate of change, so it's going to be temperature over time, so this would be degrees Fahrenheit per hour. Notice that the number is negative. The negative is important. It tells us that it's a negative slope. In other words, the person's temperature is decreasing. So the person is obviously, or seems to be, on the mend. So finding a rate of change can be a lot more descriptive than just finding a point. So again, this first question, all you're doing is finding a point on a graph. Now you don't need to draw this graph, but the graph would be some function. The point, this first question is just giving you the value at that point. It's telling you what the temperature is. The second question is giving us the slope of the tangent. In this case, the slope of the tangent is negative, so the person's temperature is decreasing. So that wraps up section 6.1, our first application of the derivative, and that is that the derivative of a function represents how fast the function is changing, and we call that its rate of change.